Hello again, this is Mr. Smith with reading quiz number 11. This reading quiz is all about improper integrals of the second type. Early in reading quiz number 10, we talked about improper integrals of type 1. Those were integrals that had a limit that involved infinity in some sense. The improper integrals don't involve infinity with the limits, but they may involve infinity with some sort of a discontinuity in the function. So let's take a look. What is an improper integral of type 2? A second type of improper integral occurs if there is some sort of discontinuity, often involving a vertical asymptote. So we say, if f is continuous on a to b with a included, but discontinuous at x is equal to b, then the integral from a to b of f of x dx is the limit as t goes to b from the left of the integral from a to t of f of x dx. Similarly, if we're discontinuous at x is equal to a, then we can say the limit as t goes to a from the right of the integral from t to b of f of x dx is our definition for this particular limit. If we're discontinuous at x is equal to c for some c in between a and b, then what we do is we split up our integral. We have our integral from a to b of f of x dx, go from the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And so we break up the integral based on that point of discontinuity. So the essential question we're going to ask is the discontinuity so bad that we can't find the area under the curve? Remember, we talked way back when about Riemann sums and about how we use those to find out the area underneath the curve. If the discontinuity is not too bad, then we can still approximate with rectangles. However, if the function has some sort of vertical asymptote that it's very difficult to get around, then we might not have the integral converge. So here's an example. Evaluate the integral from 1 to 5 of dx over square root of x minus 1 if that integral converges. So there's a discontinuity with this function at x is equal to 1. So what we do is we say the integral from 1 to 5 of dx over square root of x minus 1 is equal to the limit as a goes to 1 from the right of the integral of a to 5 of dx over square root of x minus 1. The antiderivative of that function is 2 square root of x minus 1. So keeping our limit signs, we then evaluate that at 5 and at a and use FTC. And we're going to investigate what happens as a goes to 1 from the right. When we plug in 5, we get 2 square root of 4. And then evaluating the limit as a goes to 1 from the right of 2 square root of a minus 1 produces 0. So our final answer is 4. Therefore, the integral will converge to 4. The second example. Evaluate the interval from negative pi over 2 to 0 of negative cosecant squared of x dx if that interval converges. Again, this function has a discontinuity at x is equal to 0. That's because the sine function is equal to 0 at x is equal to 0. So we can rewrite this integral as the limit as b goes to 0 from the left of negative pi over 2 to b of negative cosecant squared of x dx. The antiderivative of negative cosecant squared of x dx is cotangent. So we investigate the limit as b goes to 0 from the left of cotangent of x from negative pi over 2 to b. And as b goes to 0 from the left of cotangent, the cotangent function approaches negative infinity. Therefore, the limit does not exist and our integral diverges. Example 3, evaluate the integral from 0 to 5 of dx over x minus 4 if that integral converges. As you may notice, this integral has a discontinuity, in fact, a vertical asymptote at x is equal to 4. So we need to break up the integral at that point of discontinuity and attach our limits to it. So we have the integral then becomes the integral from 0 to 4 of dx over x minus 4, plus the integral from 4 to 5 of dx over x minus 4, which can be then written as the limit as a goes to 4 from the left, the integral from 0 to a of dx over x minus 4, plus the limit as b goes to 4 from the right of the integral from b to 5 of dx over x minus 4. Continuing, we find the antiderivative for one side. The limit as a goes to 4 from the left of natural log of x minus 4 absolute value from 0 to a. And this limit goes to negative infinity because of the nature of the natural log function. That integral immediately diverges. If we see that one part of our integral, if we break it up, diverges, then the entire integral is going to diverge, as we saw here. If we had tested the other integral, we would have gotten a similar sort of result. And finally, if the discontinuity was ignored, we would get the integral from 0 to 5 of dx over x minus 4 of the natural log of absolute value of x minus 4 evaluated from 0 to 5, which would give us the answer of natural log of 4, which is not true. This is why we need to break up our integral. Example 4, evaluate the integral from 0 to 1 of natural log of x dx if the interval converges. There is a discontinuity in the natural log function at x is equal to 0. So we apply our limits. We say the limit as a goes to 0 from the right of the integral from a to 1 of natural log of x dx. The antiderivative, if you remember from integration by parts, is x natural log of x minus x. So when we plug in, we get limit as a goes to 0 from the right of x natural log of x minus x from a to 1, which gives us 0 minus 1 minus limit as a goes to 0 from the right of a natural log of a minus a. This limit as a goes to 0 from the right of a natural log of a is trickier than you think because we have an indeterminate form. We have 0 times negative infinity. So we use L'Hopital's rule. If you remember, we did that a couple days ago. Limit as a goes to 0 from the right of a natural log of a would be limit as a goes to 0 from the right of natural log of a over a to the negative 1. That's the trick we talked about, where we write one portion of our product in the denominator. When we take the derivative of the top and the bottom, we get limit as a goes to 0 from the right of 1 over a over negative 1 over a squared. Simplifying, that's the limit as a goes to 0 from the right of negative a, which is 0. So finally, this means that the overall limit, therefore, is negative 1. And we plug in our limit here, and then, of course, this limit is 0 right here.